Okay. Just checking, you know, to make sure everything's up. I'm just gonna see right here. I need to change some information. That is a given. Okay, yeah, that's okay. Okay, so let's do that. So let's just go to YouTube real quick. Right here. YouTube. Okay. So, what is up, guys? I don't know if anyone's here yet, but I'm just here. I'm just doing some live streaming because I can. Let me see if I can just go to the live webcam streaming. No, I already have a stream going up. Maybe I just have to go to my studio. So let's do that. Okay. I don't know if this is supposed to be shown. I'm not for sure on that. I'm just, because all I know is the key is not supposed to be shown. I can tell you that. Where is live stream? Here we go. Wait. Analytics, videos, comment settings. Let's go to the classic. I don't know. There used to be like a way to go live here. Yeah, here we go. Yeah, I don't care. Whatever. Yeah. Not now. Okay, yeah, we're streaming. We are streaming. So now we can actually change this. So, interpreter, that's right. So, emulator. And yeah, it's not supposed to show that. Okay, so minor issues. Okay, I don't think it is. Yeah, okay. We go live here. Okay. We should be good now. Okay, so now I can exit that out. I have it on my phone, by the way, so, and I couldn't change it on my phone. So, yeah, I'm just gonna say, welcome to the live stream, everybody. There was a total of no one here. It's great. So, yeah, so let's just start going to it. So, yeah, so basically what we have is we have the basics. We have ourselves a HTML with canvas in it, as you can see. We also have classes, just in case we need classes. And I also got some CHIP-8 ROMs. And so these are good. I'm just going to actually get rid of this one. This one's not what we want, because that one doesn't look good. So this is the test ROM. I know that. I was looking around on the internet. And so after we do a test ROM, we have Pong, and then we have key test. And so yeah. So I guess we can begin, I guess. So let's go. So what's the first thing we need? We need to make some opcodes, I actually need a reference. So, there we go. I've actually tried this before, and so this is one of the best things to use is the CHIP-8 Cow God reference, which I really like. It's really good. And yeah, so let's begin. Let's read it. Well, okay. About CHIP-8, it's an interpreter. Yeah. So if we look at this. Okay. So, yeah. Here's the memory. Okay, so it has 4,000. Okay, it's that much bytes. But it can only start accessing here because this one's reserved for that. It has 16, and it also has a 16-bit of I. This register is usually store memory addresses. Okay, and then okay, so there's 15 general purpose 8-bit registers, and that's 0 through E. So let's make that. So class CPU constructor. So this dot registers is equal to an array, and then we can initialize later. And so I'm just gonna say registers 0 through E. And this dot, there's a flag register, so register F, and that's equal to 0. And we're just gonna say 4 flags, and then there's an I register. This dot register I, it's also equal to 0, and this is register I. For memory addresses for flags, let me say register F, and then what I would use for. Okay, so now that we have our registers, we can continue on. Okay, so CHIP-8 also has 2 special purpose 8-bit registers for delay and sound timers. I'm trying to see if the music's loud enough for the stream. It doesn't sound like it. Okay. So, yeah. So next, we also have 2 special purpose 8-bit registers for 2. Okay, so, okay. And then, so we have 2 timers. They go at 60 frames per second. And then see whatever section it was. And then we have the program counter and stack pointer, and then we have stack as an array of 16. Okay, there we go. So now we can say update timers. I'm trying to get all the functions we would need for this. We also actually need to, start timer. So delay timer, that's equal to 0, and this dot sound timer, that's or 0. Let's put that in there. Delay timer, sound timer goes every 6. Okay, I'm just gonna copy this. Okay, it goes down once a frame. And so now that we have that, we also need the program counter. Yeah, the program counter. This dot program counter, and that's gonna be equal to 0. And this dot stack pointer, it's equal to 0 as well. And then we also need an actual stack. So stack is equal to an array. Okay, I'm back. I had to do a few things like chores, and I had to also get a drink. I got myself a Pepsi. I'm gonna hold this up to the mic. Just gonna open it for ASMR effects. Satisfying. It's very satisfying. Smells like a Pepsi. So anyways, where were we? Okay. I'm just gonna put some comments here. Program. Counter, I have no idea what that does. But stack pointer. Of course, stack pointer. Stack. Maybe I can read it. And is used to store currently executing address, and so program container stores current address, and then stack pointer index for the stack, because that's what I've seen right here. And then the stack is an array of 16 16-bit values and used to store the address that the interpreter showed. Yeah, anyways. And then it should return to when it's finished with the subroutine. So this should basically store where the previous program counter was, and then the stack pointer just does whatever it needs to store it. Stores program counter. There we go. So now we should have that. Oh, there's a keyboard. Okay, so it has 16 keys. And it does 1 through F. So can we just have 16 keys? We have to have 16 keys. Okay, this dot keys is equal to, and then whatever, an array of keys. Keys. Keys, it should be 16 keys to store. Okay. So the original implementation of the CHIP-8 language used a 64 by 32 monochrome display with this format. Okay. Okay. Okay, so that's how it's done. Okay, I'm just reading this and then I'm going to explain it out loud. Okay, so there's a font. Okay, is that it? That's it, okay. So basically, the display should be 64 by 32. I've also read that somewhere, so that's why it's 64 by 32 here. And over here, and then it draws it with sprites using 815 by by using 8 15-byte numbers. Okay. And then we also have built-in fonts that we have to do. So that's pretty a lot. Okay. So what we have to do is we just gotta put this in an array. Okay, so let's do that. So we need graphics. This dot graphics is equal to an array. Graphics 64 by 32. Would you choose the? I'm just adding some more. Max 16. Okay. So Graphics. It's pretty Graphics. And what's next? We need put the font in. So we need to actually do font. This dot font is equal to this, and this is actually one that we can fill it in. Oh. This might be a little bit. 0, it ain't strings, it's gonna be number 0x50. No, excuse me. Then 0, 9, 3 times. Or 9, 0. And then that's a. So we can actually store that. So this is going to be A. We can copy this over about 16 times. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so let's do it there. So it's easier to tab over. D, E, F. It's not A, B, it's 0, 1, 2, 3, 4, 5, 6, 7. Oh crap. 8. Why do I always press enter? 9, and then A, finally. B, C, D, E, F. Okay, so now that we have all this, for that one, we now have all the fonts except they're all 0, as you can see. So 26227, 26227. It's 26227. What's 2? F1 F1 F8 F. Okay, F1 F8 F. There we go. And so now we need to 3 F1 F. So okay, so this is 1 F1 F. Okay, so F999. That's supposed to be now. I think, right? Yeah. 26227 F1 F8 F F1 F1 F. Okay. And so if we go down to, are we at 5? No, we're at 4. 4 99 F11 9 9 that should make 4. So this is how they describe it as. So it basically turns a binary number into a bunch of this, and then turns the binary into hex, and that's how you store it. Okay. It's crazy what the amount of stuff you can do with just numbers. I mean, of course you have to know what to do with those numbers, but still, store all this. So this one, oops, wrong one. This one is going to be the opposite of 2, so this is going to be F, 8, F, 1, and then F. And then this is 6, F8, F9, F. Okay, so F8, F9, that's already there, and then F. What if I do it a row at the time? Well, that would be so helpful, so assume. Okay, so it's, okay, all the beginning ones are F except for B. So B is just going to be E. And that's good for the rest. Yeah. Okay, then the second one, we are going from where? 7. So from 7, 1, 9, 9, 9, 9, 8, 9, 8, 8. So 8, 8, 9, 8, 9, 9, 9, then 1 for 7. Okay. Okay, yeah. Okay, that seems right. For the third one, 2 F F F E 8 9 F F. So F F. Wait a minute. Yeah, that's right. Then 9 8 9 8, and then E F E F. And for 9 and 8, F F 2. F F 2. Okay. Okay. What's next? The fourth one, which 4 9 1 9 9 8 9. Okay, so 8 8 9 8. Then 9 9 1 9 9 9 1 9. Okay, I'm back. I'm just getting chores. If anyone's here, that'd be nice to say hi. So we're at the fourth one. I think we already did the fourth one. 4 9 1 9 9 8 9 8 8. So 8 8 9 8 9 9. And we are not finished. Okay, so what is 8? F2. So we are not there. No, sorry. 4 9 1. So 4 9 1. Wait a minute. Might just change something. Okay, 4, 9, 1, 4, 9, 1, 9, 9, 8, 9, 8, 8. So 8, 9, 8, 9, 9, 1, 9, 4. And then 4, F, F, 9, E, 4, F, F, 9, E. And then right here is an F, E, F, 8. F, E, F, 8. Okay, so that should be all the font. There we go. That took a little bit longer than I wanted it to, but I did it. And then here's the timers again. So delay timer is active whenever the delay timer register is non-zero. So when it's not 0, it's going to go down. The timer does nothing more than subtract 1 from the value of DT at a rate of 60 Hz, which is 60 frames per second. When DT reaches 0, it deactivates. Okay. So we can actually do that in this. So if this dot delay timers is greater than 0, this, we can actually do this in one line and save some room and bytes. This dot delay timer minus. There we go. And then when it reaches 0, it deactivates. And the sound timer is active whenever the sound timer is okay, so it's the same. As long as sound timer's value is greater than 0. Okay, so it does the same thing, but if it's greater than, then it beeps. Gotcha. If sound timer is greater than 0, this is more complicated. So this belongs with some curly brackets. So now it does sound timer. It goes down, but then it also beeps. So I'll do that later. Beep. Beep. So it's supposed to make a sound, but we don't have a sound yet. So we can probably do console.log beep. So okay. And only has one tone, the frequency of this tone. So you can make whatever sound you want. Okay. So CHIP-8 instructions. It has 36 different instructions, including math, graphics, flow control functions. So there's 36 opcodes. All instructions are 2 bytes long and are stored most significant byte first. Or 2 bytes long. Okay, so it's this chunk. In memory, the first byte of each instruction should be located at even addresses. This program includes this. It should also be padded so any instructions follow it will be properly situated in RAM. Okay, so I think what it means is that, okay, so let me go to the ROM. So that this is the entire opcode right here. But the first half of it should be put in one memory location, and this other one should be, okay, so each one is 8 bits, which means that it takes 1 byte, which is 0, 0, that's 1 byte. And the second one should be in the second memory address. Okay, so when we load ROM, we should keep that in mind. And then it goes into instructions. Anything else after instructions? Super CHIP-8, I don't know how to do that. There's like no one. So this is interpreters and credits. Nope. So I guess that's it. I guess that's all of here. So we can actually start initializing. So initializing. There we go. So initialize. First thing is. Wait, we don't even have memory. This dot memory, and that's equal to that. Memory. It's gonna be 4 kilobytes, which is this number. There we go. Okay, so now if we do this, I can actually make it all even up and it looks good. Okay, so we got register F, I, and it does all this. So now we initialize. So the first thing we do is we set all of them is equal to that. Memory. All of them needs to be, so it needs to be that much memory. Well, I can't do that yet. For var I equals 0, I is less than 4096, and I plus plus. So I, or not var I, initial this dot memory of I is equal to 0. So now it creates 4096 memory spaces, and it can store stuff in it. So yeah, it's good. Now the next thing we need to do is we need to set up the registers. So registers, and there's 15 of them, and then stack as well, and that's 16 stack, because I've already initialized the numbers, as you can see, so that's good. So we also need keys. I'm gonna say keys, and that's gonna be false because I don't want them as an integer. I want them as a boolean because keys can be in either an on or off state. Graphics, I think that's our last one. Put that down there. Graphics. It's not the cursed graphics. Okay, I am back. And yeah, let's continue on. So, excuse me. What is 64 times 32? 64 to 32. 20, 48. Okay. So there we go. So we have now initialized all the numbers. So what else do I need to initialize? Oh, font, frick. In the interpreter data. So that's the interpreter data. Remember this. So it should be stored in here. Okay, so we could just start it off here. So for var I is equal to 0, I is less than this dot fonts dot length, and then I plus plus, which means that we can just do this dot memory of I is equal to this dot fonts dot I. So now we store the fonts into our memory. So there we go. So now that we have initialized, we can actually, create this. So after that, var CPU, it's going to be equal to a new CPU, and then CPU dot init. And let's check out our values. So we have that CHIP-8 emulator refresh. Nothing should change graphically, but in our developer console, can't get length of undefined and classes of 53. Wait, is it? Oh, it's just dot font. Okay, it's a little error right there. Let's clear that. Okay, so CPU. If we look through here, we have our delay timer, our font, which we have, our graphics, our keys. Keys should not be that much. I just realized that. Should be 16. Okay, let's try this again. We don't want like anything messing up while we're adding opcodes, because that's like one of the most delicate times. Okay, we got the font, and then we got it in the memory. Okay, so we're good there. We got the keys, we got the graphics, we got all the registers, stack and stack pointer. Program counter. Yeah. Okay, CPU should be good. We are now to create another class. Let's say initialize memory. Because after I get done with this, I'll probably go to put it on GitHub. And also, I really need to learn how to use GitHub correctly. That is unnecessary. Okay, I'm back. I've been doing some delivery to my parents, so that's why. So initializes memory. Should probably do it that way so I don't have to. Okay, so initializes memory, registers, search through E, initializes stack, initializes keys, and initializes graphics. Then loads font into memory. Okay. Looking at it, it says it's okay. Yeah, it's okay. Drop frames. We're going good. We're going good. How long have I been on for? 46 minutes. Okay. Always good. Always good. Update timers. We're good there, actually. Count down if greater than 0. Then do it if greater than 0. Make noise. There we go. So now that we've had this all commented, I think we are ready to now have opcodes. So we don't need the CPU for right now. We need class opcodes. And this is how I differ it from how I originally did it. Because how I originally did it, it was a switch statement and I hated it. Because there was like, no, it was so rigid that I couldn't do much with it. So if there's like a bug and I didn't know where it was, I couldn't really do much. And there was like no debugging. So now with opcodes, I can just say, initialize, because I really don't need to store anything. This opcode is equal to empty array, and then whenever I need to add a new opcode, I can just say this opcode. It did whatever the opcode is, say whatever the first one is. I think that's the first one, isn't it? Or this is the first one. Okay. 00E0. So if this is the opcode, then we're gonna say it's a new opcode. So new opcode. And we need a few things. First of all, we actually need to create a class called opcode that stores some things. So this opcode constructor, and it's gonna have the opcode. Oh wait. And then in this opcode, we need the name, and then registers. No, we can do that later. So actually we need callback. So in here we can then say run, which has these parameters like registers. It basically can manipulate whatever the CPU is. So registers, register F, register I, delay timer, sound timer. This is only going to be called once, so this is why there's going to be so many parameters. Program counter, stack pointer. Basically going to be able to change anything in the CPU. What if I do run CPU? And then it's just going to do callback of C, and then that's it. So now, or this dot callback. So now we actually store this dot opcode. That's equal to new opcode. This dot name. It's equal to name, and this dot callback. It's equal to callback. So now we can say what example, let's say 00 E0, and then example clear screen, and then function it does. Okay, so now, hey, I just popped in. What you're working on here? I guess I missed the intro. I forgot that chat existed. Sorry there. My live chat is not working. Why? Okay. Okay. Hey. Okay. There we go. So, basically, we're making a CHIP-8 interpreter, which is really similar to emulators because I'm doing a Game Boy emulator right now, and I just need to do something to take a break from. I'll just do something a little bit more simpler. CPU. So now, when we say new opcode, I'm gonna say this, and then whatever the name is, which is clear screen, as you can see here, and then whatever its function does. So function of C, and then whatever it does. So C.graphics, and then yeah, for I is equal to 0, I is less than C.graphics.link, I plus plus, and then it just sets C.graphics of I to 0. Okay. We can actually put that all in one line as you need to do, because there's 30 something and I don't want to do that for all opcodes. To test that this works, I'm gonna like actually make the run method, so run, and it gets the current opcode. You haven't even loaded ROM. There's more. There's so much more. So load ROM, and then whatever the ROM is. So now that we have, as you can see, ROM's here, what we need to do is actually split it in half, and that's actually a string. We can split it because there's spaces. Okay, yeah. So var bytes is equal to rom.split by space. So now it gives us an array of that, but then var byte 1 is equal to, but we can't do that yet. We have to just, let's just say var, let's say var mem is equal to an empty array for right now. We want to store all of it into the memory. So then for, we have 5 people in chat. What? I don't think that's right. 5 people in chat. It went from like being 2, which is just me and myself, and whoa. Well, anyways, hello people, if you're actually there. So var I is equal to 0, I is less than bytes dot length, and then I plus plus. So what we need to do now is this, we need to actually split up all of these bytes. So mem dot push bytes of I dot substring, that is not right, substring from 0 to 2, because all bytes are 4, and then we need to do push the second half, which is just 2 and beyond. Yep, I'm here. Hi Kevin, with I have a phone call that is going to be a hold on. Okay, I'm back. Phone call. Nope, always messes things up. For var I is equal to 0, I is less than mem, then I plus plus. So let me look at this memory map again, wherever it is. Here it is. So it starts at 512. So we need to offset this by 512. So this dot memory of 512 plus I is equal to mem I, and that's how we store the ROM. And yeah, so this actually needs to be set to the same thing as well. So 512. Oh crap! No, it ruined everything. Oh, it's not even easy to fix. Why? There we go. Made my heart sad. Anyways, so we got that now. Initializes, a bunch of initializing. And so, yeah. So, now it actually stores a ROM into memory. Splits ROM into 2 bytes. Splits that into 2 separate bytes, then adds to memory. There you go. So now we can actually do run, which run is we need to actually put the opcodes back together, which we need to do some bit shifting. So var total opcode, or let's just do opcode. Opcode is equal to this dot memory. Another phone call. It's probably the same person. Okay, I'm back. Anyways, RIP recording hours, the world spins on. I know. Okay, so opcode this dot memory of this dot program counter. And so this gets the first half, but then we need to combine it with the next one. And it needs to be one number. So I'm trying to do some bit shifting, because the first one is 1 byte, which means it's 8 bits, so we shift it by 8 bits to the left, I think. Which we can do that, doing that. 8. And then we need to add it together with the next one, which is plus plus, which we can do by ORing it, which is just, it's a bunch of bit operations, which I might do in a video if I can't explain it here. If you want an explanation, just say in the chat. Memory of this dot program counter +1. So this should get the opcode, just in case then we need to actually add this. So this dot program counter plus equals 2. And so now we can actually see if that works. So console dot log opcode. And so now when it's set interval, why did I do it that way? Function of that, and then whatever it is, so 60. I don't think everything just runs at 60 frames, so, or 60 hertz, but 60 frames is the same. So CPU.run. So we also actually need to load it. So CPU.load ROM. Let's do test ROM, because that's what we actually need to pass to do it. So we're at 0. That's no good. Is it loaded in? So CPU memory. It starts at 512. Yeah, it's not loading. Okay, so we need to do some testing up in here, so console dot log bytes. Oh crap, okay, there we go, fixed. So now, it should, well, if it stopped running. Okay, yeah, we have all the bytes. Okay, so that, it's getting the bytes, it's just, is it added to memory? So let's do that. And then after we do that, we're gonna console.log of mem. Which, there it is. Okay, so yeah, it's split in half. Oh wait. It's because it's a string. Okay, let's parse it. Parse int. Since it's hexadecimal, 16. Okay, it's still 0. Let's check the CPU now. Oof. That's an oof moment right there. So memory 512, and it's not there either. Okay, so it's actually not. Oh, it's less than. That's supposed to be dot length. Dot length. There we go. Length. Not links. So now if we look, yep, I can see it's already working. Yeah, we're getting bigger, which I'm not for sure if it is. So hex to decimal. Okay. So 00 E0. And that's 224. That was the first one. There we go. So it is okay. It's working. So now we have the memory loader in. So now we can get rid of all these console.logs. Okay, so now that we have that, we can now we can actually start testing it. So it gets the opcode and then it increments the counter. Okay. Wait a minute. we also need to have this dot opcodes. This dot opcodes, that's going to be equal to new opcodes. So now that we got that, it needs to initialize, so we can do it in here. Opcodes dot initialize. Initialize all opcodes. So there we go. And now to see it's working every time. So we need to do a two-string method so we can do some debugging, because that's what I really freaking need right now. Two-string return opcode.toString. First, this, since it's a hexadecimal, we need to turn it to base 16 plus, and here, and plus this dot name. Okay. So if we do that, we can actually now have a console.log. Actually, we need to say if it exists. Okay, so if this dot opcodes dot opcode of opcode, oh my gosh, is not equal to null, meaning it actually exists, then we need to print it. So console.log whatever we just did, .toString. .toString. And there we go. So now, if we run it, it only should print what? The clear. Opcodes is not defined. Oh no, I didn't initialize it because I forgot the this dot. Okay, now it should be. Okay, opcode is not defined, and it's just not defined. So I have 13. I'm guessing it's another this dot. Yeah, this dot. Okay. It's an infinite loop. Gonna have to get rid of it. Click. And now, if we go to our developer tools, it should only have all the clear screens. Okay. So that's how it works. Now we can now start adding up more opcodes. So opcodes, here they are. Yeah, this one is ignored. And then now we need to return from subroutine. Okay. So this dot opcode of 0x00ee is equal to new opcode. And what I'm gonna do, I'm just gonna copy this. I'm actually gonna make a template one real quick. Yeah, it's good. It's good. Name, it's good. And then the function is just gonna be cleared. So now we can change this to here, change that to here, change this to return. And what does return do? Now the interpreter sets the program counter to the address at the top of the stack and then subtracts one from the stack pointer. So it sets it to the stack pointer. So this dot program counter is equal to this dot stack at this dot stack pointer, and then it subtracts 1 from it. So this dot stack pointer minus. So yeah, that we have that. Yeah, so that should work now. That's what it says it does. This dot interpreter sets the program counter to the address at the top of the stack, which is the stack pointer. So this dot program counter, it goes to this dot stack at the stack pointer, and then it subtracts 1 from the stack pointer. So yeah, okay. Next one, jump address. Okay. I just noticed something. These are like conditionals. So 1 in. Okay, oof. Okay, maybe we can just do something like a... There's a gnat in my face. So it only works for 1 and then whatever it is. Okay. Actually, yeah, okay, I think I know how it works. So this dot opcode of 1. And then when it executes, it's gonna execute. So 1, 2, 3, 4, 5, 6, 7. Okay, let me count the ones that don't use it. 1, 2. Only 2 do not use these like conditionals. Okay, so then we can just put these ones in a special one. Oh, and then we need to actually run it. Okay, yeah. Yeah, okay, so when we do this, when we run, we also need these. If we go up here, they are. We need the triple N, the N, the X, Y, and the double K. So 1, 2, 3, the N, the X, the Y, and the double K. N. Actually, what if we just set them as arguments? So args. There we go. So now it takes an args. And all of them need to have args. Or at least /a. So let me update the template. There we go. So now with arguments, we can now change it. So we can actually see which one it is. So var opcode, and this gets the correct opcode, I can tell you that. And then this, we can say, wait, and then var args is equal to this, and then opcode in ands, which, and we're going to do some masking here, which just gets certain values. So 0x, we need to get the in and in, so 0fff, and then we need the next one. And I'll put these in parentheses so they make more sense. So this is the triple N. We need to get the single N, the X, the Y, and the double K. So this is the double K right here. This is the single N, and then the X, and this needs to be shifted to the left by 8 bits, and then the Y is right here, and this needs to be shifted to the left by 4 bits. And so now we get all these values, and these are the arguments. And so now with these arguments we can actually run. So it prints it and then runs it. So then dot run with this and then args. So now it should clear the screen, and then whatever the next thing is, it should do that, and then it has arguments if it needs it. And then else console.log invalid opcode, and then whatever the opcode is, plus opcode.to string 16. So now just doing a bit of debugging, so just doing that better. So now it can do, it runs it, it takes in the CPU, and it then takes in the arguments. So then we actually need to see var and then we need the MSB one, which will get the opcode, and parentheses, opcode and 0x f000. So this will get the first one, and then we need the second one. Yeah. The second one will be the N, and then the third one shall be the, okay, yeah. So second and then 3. As I say second one, as in it tests 3 conditions instead of 2. So this one tests 1 condition, this one tests 2 conditions, and this one tests 3 conditions. Okay, so there we go. So now that we have that, we can say if it's not null, if it's not, it's not cool. If MSB1 is equal to 0x 0 0 0 0, then we can actually test it. So then it should run it as normal. Then else if MSB1 is equal to 0x 1 0 0 0, Did you try? Okay. Oh, we can probably do this. So if it first test is not equal to null. Then we need to run it. We need an if. Oh crap. If. We need also an else here. Okay, so we have now established that, okay, so if it's not there, then it goes there, and it goes there, and then if it isn't, then it's an invalid opcode. Okay, so now we can do this. Console.log this, and then .to string. We need to do the same for the other three. So for testing for 2 and testing for 3. And then after all that, we can actually run it. So and then I'll run with this and args. But yeah, and then we need to add it. We also need to say, before all this, we actually need to if statement say if this dot up code, or if msb1 is equal to 0x0000, then just do it straight up. Okay, so else it would do that. Okay, so now opcode toString and then opcode run. So now we have all the conditions. It is now time for live stream offline. It can't be offline. Yeah. Okay, there it is. Okay. That was weird. My phone got kicked off. And so I didn't know if it was offline or not. Well, so we got good progress so far. Now we can actually start adding opcodes before, you know. So if it's 1, we need to, this is a jump, so jump to in. toString might be a little bit more, but yeah. Jump, and then this takes in and then so this actually says this dot program counter is equal to the first one, because the first one is the triple N. And so the next one, if we get to it, should be the call. Okay. So this dot opcode and then 2 jump in. It should be call in now. Right? Yeah, call. So call in, and so what should happen is it puts this, it basically does the opposite of return. So this dot stack of this dot stack pointer is equal to this dot program counter, this dot stack pointer plus, and then after all this we set the program counter to in program counter to in, so is equal to a of 0. There we go. Let's continue on. 3, and it uses skip next instruction if register X is equal to KK. So let's take this. So 3000, you have code 3000, X and KK. So what is this called? It is called a SE. So uses that. So if register of X is equal to KK. So and it skips the next instruction, so it adds 2 to the program counter. Okay. So if CPU dot registers of arguments, and then X is the third one, so the second. If C dot registers of that. So there we go. C dot register. Oh wait, that's right. Is equal to arguments of 4, and it should skip. So then the C dot program counter. There's no this dots. Plus equals 2. Oh crap. This is supposed to be C, 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 and C. Well, I mean, it makes things smaller. It just makes things more confusing as well. Okay. And then we need X, KK. And so now this, no, the next one is just the plain opposite. So if it's not equal, so set not equal, S and E, and then if it's not equal, skip it. Okay. So, and this is going to be 4. So what's next? Okay, 5. And that's set if the register is equal to the other register. Okay. So 5, 5, set if equal, if it's equal, then SY. So if C dot registers at that is equal to C dot registers at that, then it does skip. Okay. And then for this one, set register equal to KK. Okay. This might need one of these. Okay, so this is going to be a load X KK. Sadly, it can't really do this. I'll do the debugging later. Okay, so load, it basically says C of register X is equal to that. And there we go. And so that's load, and then so add is plus equals. Okay. Okay, so add register and then K, and then whatever it is. Yeah. So this right here is going to be 6 0 0 0, and then whatever. What is this? Is just 7? Okay. 7. Let me just. And there we go. So we have 9 of them so far, and this just plus equals. So now we are adding 8. We are having the 8. Oh, that's a lot. Okay. So this is going to be to where this actually changes the last one. Okay, this is going to be 8, 0, 0, 8, 0, 0, 0. And this 8 is OR XY. OR XY. And it ORs it and stores it. Oh wait, no, this is load. Load XY. So it's just this. And there we go. So now we have that. So this is where it's gonna start like hitting that. So 8-1, 8-2, 8-3, 8-4, 8-5, 8-6, 8-7. There's how many, and then E. Okay, so now 1. So 1, 2, 3, 4, 5, 6, 7, E. Same for here. 1, 2, 3, 4, 5, 6, 7, E. And so now we're doing this one, so it's going to be OR of X and Y. So OR is this one. Stores it in there. 2 is and then this doesn't. And what is this one? XOR, I think it was XOR. Yeah, XOR, and so that is a caret sign. And so the fourth one is add, and this is doing some special. Okay, so add. Okay, so it adds, so we need add of X and Y, and then so it is going to be equal to, it's going to be equal to that plus mod 255. So now that that happens, and then before that we actually need to say if C dot registers of A, and then 2 plus that is equal or is greater than 255, we need to do C dot register F is equal to 1, and then add a semicolon, and then it sets it equal to it. Okay, so the next is subtract. So this one's going to be, what is this one called? Sub. So if register X is greater than register Y, then I'm going to steal you. get rid of u is greater than y. So if x is greater than y, we're going to set the register to 1. I want to do this all one line, so then when I add comments, it'll be easier to understand. So else c.register f is equal to 0. And also debugging is easier here. So if c.registers a squared, or not a squared, a2, so x is greater than 3. If it's not, then it's not. Okay. And then at the end, what do we need to do? We need to actually do it. Okay, so then we need to do c.registers of a2, so x minus equals c.registers of a3. So here we go. So now that we have that, we need to do another one at 7. So I'm just gonna take this entire thing, let's say sub n. So if y is greater than x, then set it to 1, and then 3 or 2 is equal to minus c.registers of a2. So there we go. So that does sub and sub in, and now we need to do SHR and SHL. SHR and SHL. So I think the next step is trying to format it to where the x and y's are actually what the x and y's are. So I'll be right back. I have to use the restroom. Hello guys, I am back. It's just a little quick restroom break. Okay, so let's work on sub H and L. So if the least significant bit of the register X is 1, then okay, so we can do that. If least significant bit, okay, so if c.registers of a x, whatever, so and 0x0 or 0x1, which will return true or false, or is equal one. Yeah. So if it is, then we're going to do c.register f is equal to 1. Then it is divided by 2. So c.registers a squared. Is it multiplied this one or divided by? Because I read, okay. It is divided. Okay, divided by 2. And the same goes for that, except it is for the most significant bit and it's multiplied. So here we go. And I can't really say that, so shift shifted to the right 7 times is equal to 1, which then it should do that, and then it's multiplied by 2. Okay, yeah, because if it shifted to the right 7 times, then the only thing left is that one bit at the far, far left. So there we go. Now we have all the 8 instructions in. Now let's continue on. And so 9 is just like 5, except it's probably being separated by all these 8s. So 9 SNE, and 9. And then if it's not, then it is skipped. Okay, so A is you load add in for that. Okay, so this one, I'm just gonna have to use this. I wonder how much will run now that we have this. So we have this and it runs the test ROM. Okay. There we go, yeah, okay, so that really does not help. Yeah, it really doesn't help. We're gonna have to do something better for the debugging system. I'll work on that later. I just want to get a working thing right now, because I'll probably work on it tomorrow if I have time. Okay, so we need A now, which A was... What is A? A is setting a register I to in. So what is that called? Load I in. So now it's just gonna say c.register I is equal to argument, the first argument. And this one is called A. So I think these are the ones that just start. So okay, so B is jump. Okay, so this obviously I can't do that. So 0x B000 is obviously equal to this. So it jumps to register 0 and then plus n. Okay, wherever that is, here it is. So c.program counter is equal to c.registers of 0 plus argument of 0. There we go. And then C, it makes a random from okay. So now we need to create this dot opcode of 0xC000 equals new opcode 0xC00, and this one is random, so random xkk. So it creates a random number between 0 and 255, which I can do. So for I can actually just do it. So C dot registers of a of the first one, or not the first one, the second one is equal to math dot random times 255, and this is going to be floored, so math dot floor which is going to be 256. So math.flow or math.random, and then it's and with the value of AK. So there we go. So now that we have that, we need to do the drawing, which this looks like a lot. What? That looks confusing. I'm gonna skip you. So let's go on to E. Let's put D as not yet. So this is to draw, and it needs X, Y, and N. And 0x D000. I'm just doing it all here. Not yet. So now that we have that, let's move on to E, which is a bit easier. 0x, and these I have 2E, so E091, that's going to be set to a new opcode, and this one's going to be skip if x, okay, skip x. So then it's going to be if C dot keys of argument 2, wherever it is, skipping. Okay, so if it is press, then it's skipped. So C dot program counter plus equals 2. And then the next one should be skip if it's not equal to it. So skim, what is this called? A1. So A. and if it's not equal to program counter. And then now we have F's, and then that should be all the codes. So this loads the, okay, so this says, I'm just going to copy this one. Load X, and this is for F, and which specific F07. So this loads whatever with delay timer. So delay timer. It is currently 9:30. Holy crap. I'm actually gonna go to bed. So I'm going to see you guys tomorrow. This video will probably be uploaded by tomorrow, and I will show you the finished product in Wednesday's video. So bye. Bye.